Hello students. So let's see, as I said in previous class, that deflection of a simply supported beam when an eccentric point load is acting, so use of double integration is a laborious method. So we have not gone for the theory part of it, and we have directly solved the questions, okay, in your previous class. Let us consider a simply supported beam with a point load. This as a span support A, this is support B, and this is a span A, and this is some load W active over here. Okay, now uh, this A is from the left end, okay, and B is from the right end. So reaction for such case, okay, what will be RA and what will be RB? So when you remember your previous semester, so when you calculate reactions, we will get RA is equal to W into B by L, and RB is equal to W into A by L. Okay, this will be your reaction when such load is acting over here. Now let us consider what is the bending moment at any section between A and C. This is point C. So what is the bending moment at any section between A and C? So let us consider any distance x. Let us consider any distance x from the support A here. Okay, now when we consider such distance, so what is the moment at this particular point? So let us calculate the moment. So moment at any section x from the support A, that is, we can write it as RA into x. Okay, and RA, what is RA? RA is nothing but W into B by L into x. Okay, so hope this much is clear. So moment at any section x is very simple. Just consider the left part and you will get the mx here. Now this above equation, it is true. Okay, it holds good for the values when this x is varying from here, it is 0 till A. Okay, 0 to A. So this is true for this particular region. And the bending moment at any section between C and B at a distance x from A. Okay, now when we have to write what is the bending moment if we consider this section at this particular point. So what will be the bending moment if you consider any section here? So how we will going to write the equation? So let us write bending moment between C and B at a distance, this is important to understand. Okay, x from A. Now the same distance we are carrying. Now our next section is here. Okay, at any distance x. So how our equation will change? So we can write the same equation as m of x is equal to, how you will write? Again you will write load into perpendicular distance. Okay, this is, we are taking moment at this point. So RA into x, we will write RA into x minus W into, now this is x, okay, and this distance is A. This distance where load is acting from the support A, that is the A distance. Okay, so we can write minus W into x minus A. RA, now RA we can write it as WB by L into x minus W into x minus A. Okay, so for this particular equation, now this above equation of bending moment, it is true for all the values of x between x equal to A and x equal to B. Okay, so it is true, it holds true for all the values of x between x equal to A and x equal to B. Now bending moment for all the sections of the beam can be expressed. Okay, bending moment for all the sections at any section of the beam can be expressed in a single equation. So by using this particular equation, we can actually calculate bending moment for all the section of the beam can be expressed in a single equation, and it can be written as m of x is equal to Same equation I am writing, just see the way I am writing here. W into B into L into X. Okay, now here we are just separating it into two parts. Okay, so we are just drawing a dotted line over here, and we are just separating it in other part, writing it this side, minus W into X minus A. Okay, so here this dotted line, it shows that for any point, between A and C, okay, so half part of the equation, it holds true for any point in between AC, okay, and for any point between BC, we have to add the other part of the equation. Okay, so when we need some part, we need some calculation for this part, use only half of the equation here. Okay, so I hope this is clear. Now the bending moment at any section, now we know the formula that bending moment at any section is also given as, any guesses what is the bending moment at any section, what is other formula we use? So we use the equation as m equals to ei d square y by dx square. So let us name it as equation number 1. This is equation number 2. Now equate equation number 1 and 2. When we equate equation number 1 and 2, so we can write ei d square y by dx square is equal to w into b into l into x, then this dotted line, minus w into x minus a. Okay, so write it as equation number 3. Now we are going to integrate this equation. Okay, so integrate above equation, integrating equation number 3, we get ei d square y by dx square, it will become ei dy by dx, then wb, then we can write x square by 2, then this part here we have to understand that we have to integrate it as a bracket, we are not going to open the bracket. Okay, so we will write w into x minus a square by 2. Okay, so remember this part here for this particular method. So after integration, ei dy by dx is equal to w into b by L x square by 2 plus, here constant of integration will come, then this dotted line, then here x minus a square by 2. Okay, so we are going to integrate is like this. Now here C1 is constant of integration, and this constant of integration should be written after the first term. Okay, we are writing it here, not after this end. So remember this. And I already told you that bracket should be, we have to bracket the whole term over here. Okay, we are not separating it. So name this equation as equation number 4. Now again integrate equation number 4. Okay, integrate equation number 4 equation number 4 once again. Equation number 4 once again. So with this we can write, now it will become ei into y. Okay, when you integrate this part, it will become e into I into y. Then here it will become wbl x cube into 3. Okay, plus c1 into x plus one more integrating constant, integration constant will come, that is c2. And this part minus w by 2, it will become x minus a cube by 3. Okay, so let us integrate it one more time. So ei into y is equal to w into b by 2l x cube by 3 plus c1 into x plus c2 minus w by 2 x minus a cube by 3. Okay. Now this is giving us equation number 5. Let us name it as equation number 5. And C2 here is a constant of integration. So the constant is written after C1x. Okay. We have written it after this C1. So we have written all constant at one side only. And here you have to also remember that how we have integrated it. We are integrating the whole term in this. Okay. So this type of integration is justified here because the constant of integration C1 and C2 are valid for all values of x. Okay. Now the values of C1 and C2 we need to calculate. So we have to calculate what is constant of integration. So the values of C1 and C2 we can calculate using boundary conditions. So let's go to next page. So let us consider calculate C1 and C2. So for this we will be using boundary condition. So what is the first boundary condition? Let us consider at x equal to 0, y is equal to 0. Okay, this is our one boundary condition, and second boundary condition we will use at x equal to L, y equals to 0. So how did these boundary conditions came? So if you remember our beam, it is we are solving this problem for some eccentric beam, right? Eccentric load, sorry. And when this beam is deflecting like this, so at x equal to 0, y is 0 here. Okay, at x equal to 0 there is no deflection, and at x equal to L at this point also there is no deflection. Okay, so y is 0. So we are using this boundary condition. Now let us use first boundary condition. Okay, so we are using first boundary condition now. So at x equal to 0, y equals to 0. Now let us substitute these values in equation number 5. Okay, so the latest equation what we have written, so we this is the equation number 5. Okay, this is the equation number 5. So here we are going to use the boundary condition, that is when x equal to 0, y is equal to 0. So when we substitute here the values x equal to 0, okay, so we are left with nothing, but we will get simply because so here x will become 0, y will become 0. So we left with C2 equal to 0, okay, in this particular equation. So here we get C2 is equal to 0. Now using second boundary condition. So here at x equal to L, y is equal to 0. Now again substitute this in equation number 5. So when we substitute these values in equation number 5, so we arrive at C1 is equal to minus WB by 6L, L square minus B square. Okay, so this is, we get it as equation number, let us call it as 6. Now substitute this C1 value in equation number 4. What is equation number 4? Let's see it. This is our equation number 4. We have the C1 value we have calculated just now. So let us substitute it here and rewrite the equation. This is our equation number 7. Now equation number 7, this equation you can see here it is dy by dx. Okay, so this equation is actually giving us slope. Okay, so this equation it is giving slope at any point in the beam. Now we know that slope is maximum. Okay, slope is maximum at point A and B. If you draw a tangent here, so slope is maximum at this point. But what is the value of x is at this point? X is equal to 0, right? So substitute x equal to 0. So you have to understand what is the next step, what I am doing here, okay? Because at A and B point slope is maximum. Slope is maximum at A and B. So substitute x equal to 0 in equation 7. So we can rewrite the equation as EI theta A is equal to W into B by 2L into 0 minus WB by 2L, L square minus B square minus WB by 6L, L square minus B square. So theta A we get it as minus WB by 6EIL, L square minus B square. Okay, so this is the value of theta A for this particular case. Okay, now let us substitute values of C1 and C2 in equation 5. Okay, so I have shown you equation number 5. So substitute C1 and C2, C1 and C2 in equation 5. So we can get the equation. We get the equation as EI into Y is equal to WB 6L x cube plus minus WB by 6L L square minus B square into x plus 0 dotted line minus W by 6 x minus A cube. So this is our equation number 8. Now equation 8 gives us, you can see this is y, right? So equation number 8 is giving us as a deflection at any point in the beam. Now to find the deflection YC, okay, now we want to find out what is the deflection YC under the load. So substitute x equal to A in equation 8 and consider the equation up to the dotted line as point C. See, now if you want what is the deflection at this particular point, now this is A and this is B. So in this, now this equation is valid for deflection at any point in the beam. But we know what is the deflection at this particular point. So simply substitute x equal to A and only half part of the equation we are going to use, because this deflection for this particular, the C point is coming in the AC part. Okay, so we can use the half part of the equation here. So hence we can rewrite the above equation EI. So deflection at C, so we can write it as YC, W into B by 6L A cube minus W into B by 6L L square minus B square A, which can be simplified as W into B by 6L. We can take out the A square minus L square plus B square. More simplifying it, L square minus A square minus B square. So we can again rewrite it as minus WAB by 6L. So above equation we can write it as A plus B the whole square minus A square minus B square. This A plus B the whole square is nothing but L. Okay, we have simply trying to simplify it. So then further we can write it as, I'm just continuing it from here. So we can write this as minus WAB by 6L. Then A plus B square is nothing but A square plus B square plus 2AB minus A square minus B square minus WAB by 6L. Then you can see you can cancel these terms and you will arrive at 2AB. So with this we get it as YC is equal to, so this 2, what's the 2, 2, 3 so we can write it as, and this EI will go this side, right? This is EI into YC, I will write better. So we get it as minus WA square B square by 3 into L. So finally we get minus WA square B square divided by 3EI into L. Okay, so that's how we have arrived at the deflection at point C. Okay, so hope this is simple method, little lengthy, but hope it is clear to you. So what we have considered till now. Okay, so we have considered first this particular part. We have initially we have first calculated the reaction, then we have considered a section over here, and then we have calculated what is the moment here. Okay, once we get the moment equation, then we have used, okay, we have used the what is moment at this particular part, and then what is the moment at this particular part. Once we get the whole equation, then we have indicated it as equation number 1. Then we have compared it with bending moment equation already, what formula we know. When we compare, we arrive at the first equation. Okay, when we equate this, then we use this equation, we integrate it once, and we again keep it in two part. And what you have to remember that the constant of integrations are in, we are writing it in the half part of it, okay, before the dash part. Then in next part, we have used the boundary conditions, okay, and we have calculated what is the C1 and C2 value. Once we get C1 and C2 value, we have substituted it in the equation, and then we have arrived at what is slope. So we have calculated slope here, and then we have calculated deflection. Okay, so hope this class you understood this theory part, and thanks for listening.